Okay, sorry for the delay. My computer has decided to absolutely crash. Super cool, not annoying at all. All right. So you're turning in homework 2 today, right? Who had problems? Who came to office hours? Who came to office hours on the last day? Okay, are there other office hours? When would you find those? On the syllabus. Very good. Now you're learning the trick answers. Okay. Are there any other ways to contact me?
Yes.
Which are?
Email and Slack.
Email and Slack, because you could ask a question at any time, right? And so if you choose to wait till the last minute, it's right. Right. What did I say in the first class that you'll need in this one, since we're doing ungrading? What are the motivating aspects you'll need for this class to succeed? Self-motivation. Another word was close. Discipline and accountability. So we are not maybe athletes in this classroom, but we are going to work on our minds. We're going to become excellent swimmers of fluids intellectually. Okay. All right. And then we'll be able to understand cool things about Oreos. So this is in fact from a published paper, a real study. I didn't write it. It just is my name on this cropped image. If you want to know about this, this is Oreology. It's not a real field, but when you name your own papers, you can name them whatever you want. I had a colleague recently write another one derives the dust. Because you can just get away with that. One of my friends just published a paper actually today. And he says in the very first line, Venus, so hot right now. So you can do whatever you want in science, as long as it gets by a reviewer. And what you're looking at here is the top is rotating. Has anyone ever done this? Who's not eaten an Oreo? Okay, make sure there's no aliens in here. So what you do with an Oreo, what's the correct thing to do?
Just eat it. You rotate it.
Okay, raise your hand for rotate it. Raise your hand for dunk it. Raise your hand for just eat it.
I'm going.
Get out. Just kidding. Okay. So some folks, right, what you want to do here is you just want the what is called stuff, S-T-U-F, not 2 F's. And that's this middle layer. And so what you do is you rotate and then you scrape it off with your teeth. Has anyone ever experienced this? And then you leave those 2 sandwich pieces, you put them back in the container for the next unwitting recipient. Okay. It's hard work, but someone has to do it. So what you see here is this is the cream, and then this is the wafer. And what they do is they rotate the top wafer, and they hold the bottom wafer fixed. What are they testing here? How much cream will get on the top wafer? It's actually the bottom wafer, but this is absolutely correct. What they're looking for here is the distribution of where cream will be located after spinning the top, whether it be totally mixed up, whether it will break, shear off in certain locations, or whether it will just pop right off. Because what is this telling us? This is telling us something fundamental about the cream. It's telling us about the way that velocity is transported through something that roughly resembles a fluid, right? Now you might look at that cream and say, that's not a fluid. Remember, everything's a fluid because you can't stand on that, right? So in fact, when you spin it slowly, you can transport a velocity differential. Here it's moving quickly, there it's not moving at all. And you think, well, that's really stupid. You're just getting me excited about the day, talking about candy that I don't have. But in fact, you will see the same concept again when we talk about rotation, we talk about stresses and strains. Okay? So I was very fortunate to happen to find this yesterday. Okay. Okay. We were talking about kinematics, which is the study of how motions move without respect to the forces pushing. We haven't developed any equations of motion. We haven't developed any Newton's laws or equivalent to that. So we're just talking about how do we use the tools and what do we need in order to describe the fluid itself. And one thing that we have to check is that under a Galilean transformation, our rules make sense. Okay. What's a Galilean transformation? Raise your hand. Yeah.
You go from like stationary reference to like a moving.
Correct. So if I walk from left to right, okay, and I'm throwing this up and down, I catch it just as though I'm doing the same thing while standing still. The physics is invariant. So if I were moving and I throw it from your reference frame, you see combined velocity. I don't. I see a reference velocity that just goes up and down. And there's a way to connect these two frames. That is the Galilean transformation. To go from a coordinate system that's moving, one that's not moving, one that's rotating, one that's offset. Those are all transformations of the coordinate system, right? Okay. So up here, you have a stereotypical example of fluid going past a rock. We've seen this, right? And the streamlines, what's a streamline? Tangent to the velocity. One extra word we need there. Instantaneously. Okay, that's the only caveat for a streamline. It's like a snapshot of the flow. What are the other ones, by the way? Okay, what does that mean? What? Is that a streak line or a path line? That's a path line, right? That's the whole life of a particle, single parcel, right? Well, what's a streak line? Yeah.
Curve that connects all of the particles that both have.
Right. So a fixed point in space, it connects everything that's going to go through it. Right? Okay. So in this particular circumstance, I'm watching a parcel of fluid from the left, and it goes around the rock. Okay, and that's the streamline. Right? The fluid flow is to the right. So U is positive in the right direction. But now let's move along opposite to the flow, and imagine that the rock is moving to the left and the flow is not moving. Suddenly, the streamlines look like this. That's blasphemy. Well, of course, that has to be the case, right? Because if you're moving to the left-hand side, this flow would not appear to move, right? So this is the way the fluid looks like it's moving when you're moving left to right with the rock. That make sense? Okay. Unfortunately, if you look at the top here, A, this is a form of steady flow. Whereas if you look at the bottom, B, this is unsteady flow. How did that happen? Yeah.
Fundamentally, just because the frame of reference is also moving with the rock?
Correct. The frame of reference is moving with the rock. And when we go through that Galilean transformation, we will see in our total derivative, what was the total derivative again?
Gradient of F in the direction of U. It's not U.
Okay, gradient of F in the direction of U. Like that?
Yeah, and then. Also, df over dt for unsteady. That's like the unsteady. No, what was that?
Partial F, partial T. And which of these meant what?
The gradient f dot u is the advection. And the partial f over partial t is the unsteady. You know what the second part was?
Right. That's okay. Okay. So in fact, when we do a Galilean transformation, we're not going to do a lot of them. You'll see some of them, but you just need to internalize the idea that unsteadiness versus advection, they can play with one another. What I mean by that is that you can transport material, right? Or you can say that the flow is changing, unsteady with time. You see that might be the same? If you're moving in the direction of the flow. If you're moving in the direction of the flow, the advection doesn't look like advection anymore. It looks like the flow is changing with time. You see that? Okay. Yeah.
What was your definition of Gaussian transformation again?
Yeah, it's a good question. Thank you. What's the definition of a Galilean transformation?
We only have one target.
But we'll change it in like now. What's the definition of a Galilean transformation? Yeah.
Being able to transition from a stationary frame to frame.
Does it have to be in motion?
Uh,
No, it can also.
the opposite effect, so it could be.
You're halfway there. You're halfway there. Motion is good. Hold on, someone help him out. Okay, what's another way to say that? Rotation. Okay, so we could go like this. That's a good Galilean transformation, right? Oh boy. Okay.
So when you go from a stationary to a rotating axis?
Doesn't have to be rotating. Any transformation between two reference frames is a Galilean transformation. Okay. Why does it get that name? Figured it out. Do stuff long time ago, get your name on it. All you have to do is go back in time. Okay. So in fact, you can connect these. So you could say x prime equals x plus v in the x direction t. You ever seen that before? Looks a lot like a kinematic equation, but this is describing how the new x prime coordinate works. And of course, you can go back and forth. Right? Okay. All right. So speaking of, we have some stuff that you're going to hate. Tensors. Now that word sounds bad, but it just means matrices of how many dimensions? Yeah, that tells you how many. Usually more than 2, right? Matrix is 2, vector is 1, tensor is like 3, 4, 5, right? Okay, we're not doing general relativity, so they're not going to be awful, but we will need to understand them. If you're thinking about it in computational terms, just remember, this is an array with 3 dimensions. I can do it. Okay? Okay, so we need to consider the ways that a fluid parcel can deform. And this is going to take us back to a couple different ideas. First is this idea of stress. When we first talked about the idea of stress, we were talking about it with respect to something called viscosity. And almost unanimously, people did not like my explanation of the viscosity and how stress is transferred. So I want you to imagine something really quickly. This is the pitch drop experiment. Okay. The pitch drop experiment looks like this. Okay. So they remove a little cover at the bottom, they pull it out, and the fluid does what? Drips out. Good. Okay. If it were water, what would happen?
Like,
Flow out quickly. Pitch, however, flows out slowly. Now, if I take a globule of pitch, okay, and I hold it, say, 5 feet over the ground, and I drop it, what happens? It falls. So what happened? There's a major difference here, right? If I drop water, okay, it falls. A pitch is not going to stand there doing nothing. So we missed something really important, and that's talking about stress. So when we talked about stress earlier, I drew something like this. Okay. And this was, for example, u of y, and this was y. That the speed were increasing as you went higher into the fluid. And people were like, well, I really don't get this explanation. You have this rate of change of velocity. How is that represented with viscosity? What a stress is saying is how is the fluid redistributing that velocity change? Okay, so for your pitch, what's happening? What's the forces on it?
For what scenario?
The pitch on the left-hand side.
Okay.
All right, let's do the right hand. Right side will be easier. Free body diagram.
Yeah, forces of gravity, downward.
Okay, so just mg. Any other forces? Okay. Come on, let's see that. All right, what about this one?
MG.
mg, very good.
The force of the walls is a.
So there's the force of the wall, the normal force, pressing up into the fluid. And what is it doing? Not friction. It's distributing the velocity in the direction, right? It's transmitting those forces throughout the whole fluid. Because if the viscosity is low, right, that function is small, then it goes right through. There's no stress on the fluid. Whereas if it's high, it can transport that velocity differential quickly. Does that make sense? So confusing.
So high velocity. So the fluid has high viscosity, then it transfers velocity throughout the substance slower.
Quickly. So what I mean by that is this is going to go counterintuitive, okay? So if I move my hand over something, and you move through it very quickly, you're like, well, okay, then you redistributed that energy well. No, just got out of the way. Whereas here, the velocity is being distributed quickly throughout the body. So you try to push on it and you cannot. Viscosity is high.
It takes up the velocity.
It takes it out of your hand. Right. So for the same force, right? Those fluid particles get out of the way. They can't give you the back reaction. They get out of the way for water. For pitch, it says, no, I'm all here, baby. So you try to slide over it, and it takes all of that force and it puts it into the entire body. You see now? You see what I see?
It's really counterintuitive.
Yes, correct. Welcome to fluids. It's fucked, but we're gonna see it a couple more times, right? And in fact, we're gonna see it so many times that I will wager $3 that you will understand it in 3 weeks.
Okay.
$3. I don't know. I didn't actually want to wager that, but I think you'll get it. Okay, so look at this. This is the word stress, and not what we're feeling on a day-to-day basis, but what the fluid is feeling from an outside transfer of velocity along a differential gradient. Okay, so you have a gradient in the velocity, and we're transporting that through the fluid. Okay, so what's strain? What's that?
It's just like squishing.
Squishing it. And what else?
Squishing. And it's overall changing the shape of the particle or the volume?
Okay, so there's 2 ways to change something. You can squish it and stretch it. Very good. Okay, so that's the hidden part of strain, is the anti-strain, pulling it apart. All right. What's rotation?
Exactly.
right? No distortional change. You didn't see my leg. Okay? So the latter are described by velocity gradients, piling up versus rarefying. Okay? So how do we write these in terms of the strain and rotation tensors? Okay, well, we got to have our book out because I never remember how to write these. That's okay. All right. So we're going to define. Let's go over here. You guys like index notation? Okay, you're gonna love it. Okay, du dx. Okay, now I kind of wrote something really similar to that over here, right? So u and u, we're gonna add a little caveat. Now it's gonna be u in a certain direction, but I'm gonna do that arbitrarily. I'm gonna do that with this u sub I. Okay, and I'm gonna go down here. I'm gonna say this is the distance. I don't care which direction. I'm gonna do x dot j. So what does that say? Okay. What's that? Yeah, so I and j, right now, we're assuming they're different, right? If it were I, then I would write this as, right, that would be I. Versus sometimes we think of it in terms of let's say I use u, v, w for x, y, z. Okay? That would be u, dx, or could be v, dy, or dw, dv. You see how that's all the same? So the only thing that I'm going to do is I'm going to call this I. I'm going to call this j. Okay. And now immediately forget that. Okay. So I've just written this form. And this is talking about what is the physical representation here?
The rate of change of the fluid velocity
Rate of change of the fluid velocity.
in the I direction,
Mhm.
how it changes in the x of j direction.
Almost. It's the rate of the fluid direction in I, how it changes in j. Good. Okay. We just said, for example, the rate of change of the fluid velocity in the y direction gave us our, what was this thing? Stress. Okay, so in fact, we're going to define things like strain and rotation using these bad boys. Okay. So I'm going to write something really fun and very meaningful. Okay. This will be something we call S I J plus 1/2 R I J. What's S I J? Close. What? Strain. So this is the strain tensor. What's this? What? Rotation tensor. Oops. Okay. Ta-da! Oh, I'm just kidding. Doesn't matter, yeah. Okay, so what does Sij actually look like? Well, it's in your book, but I'm going to write it here. Sij is a funny combination of du I over dxj plus duj over x I. And the rotation tensor looks like B U I E x j minus E U j over D. First thing I ever did. Okay. So by inspection, write down for me what R00 is for a fluid. What? Let's see if you get this. Let me know when you have it. Raise your hand. Okay, what is it? 0? How many people think 0? Everyone thinks 0? Anyone lost?
Yeah.
Okay, what's losing you here?
Copy it down.
Oh.
I haven't thought about it.
Okay. So it's in your books. You don't have to copy it down. This is equation 311, 312, and 313. Maybe I should have said that. Don't write this down.
Well, I'm already there.
I'm already there. I'm already committed. I'm committed. Okay, so what about this one? So this is IJ. So for 0, 0, I have du0 over dx0 minus du0 over dx0. Oh, perfect. That is 0. What is S0, 0? It's what? 1? It's not a number. It's not a, hold on. You guys, you're jumping way ahead. Okay. So you thought this one's 0. This one must be a clever answer. Okay. So S00 is. I think not 0.
D0 over DX.
dx0 over dx. 1/2 du0 over dx0 plus du0 over dx0. There's 2 versions of that. They cancel with that, and you just have 1. Oh. So I'm going to say this a little different. Okay. S00 is the rate of change of the velocity in the direction of that flow. Right? So it's the rate of change of x in the x direction. What would that be? That's how you would interpret it definitely for a physical particle. Think about it in a fluid. Let's say for example here, the fluid is decreasing in flow in the x direction. What's happening to the fluid? It's not spreading out, it's flowing down, compressing, it's piling up. So we talked about these 2 things here, right? We're talking about strains as compressions and distortions, right? This is pushing the fluid together in this direction, right? Right? Okay. We're going to get a sense for all of these terms.
So this fluid would be like air and not water, right?
What?
This fluid would be like air and not water.
Doesn't matter. They both work. We'll talk about the compressibility of air. And it's funny. It's mostly incompressible. But it's mostly incompressible. Surprisingly. For like physicists. So okay. All right. So we talked about equations 11, 12, and 13, defining the symmetric and anti-symmetric tensor terms. Now, how did I know it was anti-symmetric? What does this word symmetric mean in terms of tensors?
That's the multiples of diagonal, right?
Multiple. Same across the diagonal.
Yeah, I think you're both saying the same thing. So this would be a symmetric tensor, right? Let's say I have 9 values here. How would I write it?
Would be like
A, B, C.
and then everything else zero.
Could be 0, but it could be anything.
Oh.
But it would have to be D, D,
Um,
E, E, F, F. That's the definition of a symmetric matrix, right?
Mhm.
Now, F and E can equal each other. In fact, they can all equal each other, but it has to look like that, right? What about this one?
It just had a bunch of random values for.
Nope.
The opposite.
This way, flip signs.
There are flip signs. Down the diagonal, there's what? Nope.
Here.
Why zeros? Look over there.
Did you equal the?
I already told you that was anti-symmetric, right? So it has to be. If I have 0, 0, 0, if A, B, C. What? Because that's how I'm filling it out.
Oh, like it would be A, B, C, because anti-symmetric and non-symmetric, are the same thing.
Well, yeah, so what's the relationship between the different parts of a symmetric tensor? So look for a second at the anti-symmetric tensor. And I want for you in your head to write 1, 2, and then write down 2, 1, and look at how they're related. The one on the right-hand side is anti-symmetric. The rotation. Is it what? Negative 8. Correct. That's the relationship between them. Right? Okay. So these are symmetric and anti-symmetric tensor terms. SII. We just talked about lengthening or compressing the fluid element in the direction of motion. SIJ is a shittier one. Okay, what the fuck does SIJ mean? SIJ is the rate of change of the fluid, let's say the U direction fluid or the Y direction fluid, in a different direction. Let's say the V, which would be our Y, which was Y? X, Y. Okay, let's do Y this way. Okay. So fluid's going up this way, but it's changing in that direction. Right? It's a different form of stretching, right? Okay. And it defines the rate at which I and J, directed fluid elements, are heading towards one another. So you have a fluid element this way and a fluid element this way. Are they heading towards each other? Well, they are if there's an SIJ term. If there's a negative term, then it would be heading away from each other. So we're talking about, remember, we think about it in our minds, an Amazon package, beautiful Amazon package that we're rotating, that we're translating, that we're squishing, we're expanding. There's lots of ways to play with this Doritos bag or whatever you want to call it. Okay. SIJ defines the rate at which fluid elements are headed towards one another. So let's say I take this fluid element, squish it. Right? What if I take a fluid element Like that. Well, imagine that was drawn perfectly. Really good, right? What an art piece. Okay, this is the same fluid parcel. I've squished the X and the Y pieces towards each other. That's your SIJ terms. Okay. You ready? You're gonna do it now. Oh, no. Questions before we do it?
So
Yeah, go ahead.
this can be thought of in the same terms as like a solid that's undergoing stress and strain.
Not really.
Okay.
There are a lot of similarities and the math will look similar. But remember, the most important thing about fluids don't pop back. Right? So when we distort when we distort a solid, it goes back to its original location. When I distort a fluid parcel, it's distorted. Right? So it's going to take that force and it's going to continue to propagate that force forever until it dissipates it in some way or another. So once I distort the fluid parcel, it's just distorted. Does that make sense?
Diamonds in terms of thinking of the fluid as like a solid collection of vectors.
Yes. So when we're thinking here, whether you think about it in the Eulerian viewpoint, or like at a fixed point and see how things change, whether you think of it in terms of Lagrangian following a parcel, we have to think about all of the ways in which that fluid parcel that we're following can be distorted. Right? And it turns out there will be some ways of viewing the fluid parcel that are the same. So for example, if I rotate the fluid parcel, the rotation tensor, that's the same as rotating your reference frame, right? So it's the same type of math. But if I rotate the fluid parcel, okay, and I don't rotate the coordinate system, that has to show up somewhere in the mathematics, right? Whereas if I use a Galilean transformation, right, and I don't rotate the parcel, now that has to show up in the mathematics as well. Does that make sense? So what we're doing here is we're connecting some things that we see in a fluid, like its ability to rotate, our ability as an observer to rotate, and we're giving them mathematical terms so that the words will look the same no matter which frame we view them in. Now, they will become differently important. So for example, stresses and strains might look different in a rotated reference frame, right? Right? Okay. Last questions? Okay. So write down all the ways in which the fluid parcel on the left becomes the fluid parcel on the right. Who's done? Raise your hand. Who doesn't want to start? Okay. If you don't want to start, raise your hand. Raise it higher. Okay, find someone who does want to start and compare answers. This problem.
But if they don't want to start, they don't start. So they don't have an answer, right?
What?
If they don't want to start, they haven't started, so they don't have an answer.
Exactly. So the people who don't have an answer, talk to someone who has already started, has some form of an answer. Okay, I'll be back in 3 minutes. Hold on one second.
I mean, I'm assuming. Yeah, I don't know. So if we were to make this as a matrix, if it's gonna be, wouldn't it be across the band? Because as I define the way that what's mentioned. So. Just perspective.
Oh,
Would
what's
be-
wrong?
would
Yeah.
be-
I don't know why I thought of it being one place for anybody.
Yeah, I don't.
And.
Well, A, B, and C, or the point A and B were like.
The bottom left corner, starts off, that part of the parcel that I mentioned, horizontal, it is the blue one. Yeah, so it starts off with the horizontal blue is all here,
First the whole box mixed up.
and then it starts off with you two upwards. And then that's that corner, more to the left, that's what we get.
One.
Okay.
Back then, like, it just fundamentally.
Plus, W.
That's why we get
Delta of one.
E is the velocity kind of fund says that, okay. Gives us the, and then same on the bottom again, you one D, which is the velocity. It's the horizontal distance. That's just for point B, there's nothing really just changing. It just. But then for point, the top left corner and the bottom right. They both have different fluid velocity. And it brings them together. This is. For the rightmost point. Yeah. Let's see if there's any.
Yeah.
Yeah, it's really like a solid.
Yeah. Which I think is.
Yeah. You can definitely have to agree that this is.
Yeah, and I think that's actually these times of it's the part where all compression would be. It's not that that's what it's right. It's the X and Y, right, and we're doing it in one, and then the other corner, we're doing it from.
You don't have to do it. I just asked you to describe it.
Okay.
There's the same equation.
Yeah.
Okay,
So it means there's no.
all right. So there are 1, 2, 3, 4 ways in which this fluid parcel is distorted. There are more than 4 groups. You will give me just one, raising your hand, I'll pick it, okay? So if you have the easy ones, you want to go first, you raise your hand quickly. Go ahead. Specific, hold on. So we're gonna be very specific here. So I'm talking about what is the actual thing that happens. The compression, that's a very broad term, right? That's the whole stress tensor. I'm talking about which terms specifically is happening here. Yeah,
Translated out to the right.
okay, so that's 2. Don't cheat.
Sorry,
Okay, so that was translated up. What's the other one? Raise your hand, yeah.
Translated to the right.
Translated to the right, good, we got halfway there.
Wow.
Okay, what else? Yeah. What?
Oh, rotated slightly, clockwise.
Okay, interesting. So where's the rotation here?
The rotation is only for the y-axis is rotated clockwise slightly.
The y-axis is rotated like that?
Yeah.
Okay. And then what happened? Last one.
Yes. So rotated counterclockwise,
It's you rotate counterclockwise, you're just back where you started. So it can't be another rotation. Yeah.
Experiences a strain,
Experiences what type of strain?
vertical strain.
No, we have the terms here. They're all around us. All around us. I even already drew it on the board. Oh shit! It's over there. What is that strain? It is absolutely strain, but what strain is it? Distortion is not a word. We're not going to use distortion. There's stresses, strains, and rotations. This is a strain. Which strain is it? Okay, so this was Y, and this was X. Yeah. Are strains symmetric? Let's go back one step here. So all strains are by definition symmetric. And rotations are anti-symmetric. Right? Okay. What did Sij mean versus Sii? What is, say that again? Towards each other. So Sij means I and J are moving towards each other.
Positive.
Positive strains. Away would be S, right? Negative would be Sij.
So it's positive strain because
Right. So what is the strain on this body?
And a negative rate.
What is the stress? What is the strain? What is the tensor term? Let's use different letters here. We have some coordinates. SYX or SXY. They're identical by definition. So to get from here to here, we did 4 things. First, we moved it, and then we moved it again, and then we switched it, and then we rotated it. And yeah,
is it just
very good question. Notice now we have a problem. Okay, so the question was, did we rotate it or did we strain it? Right? It looks like you can do either one and it doesn't matter. Right? It's a choice. Just like it doesn't matter if I move it up and then over and then up, or if I squish it all over here and then move it. Yeah.
Can you even up include rotation, or can we just say that it's getting?
Very good question. Can I do that without rotation?
One of the sides still be aligned with an axis without the rotation.
Exactly. So because this is no longer aligned with X, there had to be a rotation where the X direction here is now associated up here. Yeah. Yeah.
If it's 2 letters that are moving towards each other.
Mhm.
So S X Y X. If it was S X X, what would that mean?
Right. So let's look over there for a second. What is SXX? So let's think about it in terms of excuse me, let me say this differently. Du dx. So we talked about the fluid in the direction of X is changing with X. And we called that compression. It was piling up, right? So we said that that is compression or rarefication, right? So when it's in the direction that the flow is in, you're doing this, right? Versus if they're counter to one another, it's how they're moving towards each other or away from each other. Yeah.
So whenever there is like a Sij, one of the elements will always be on an axis.
If you just have Sij, yeah. So if I wanted to do, let's be very specific here. If I took this parcel. Okay, and I perform no other changes to it, then this would be the parcel later.
How do we know which one is going where? Because it could also compress to the y-axis. How do we determine whether or not?
Very good question. Are these pictures the same? No. Why? I mean, yes, of course. Sorry, that's not the right way to say this. Yes, they're not the same, but in which ways are they not the same? Because the axes are different. Right? It is absolutely the case here that this original axis and this original axis are now squished towards one another, but there must have been a rotation in the fluid parcel. Right? Is that clear or no?
Well, I just want to know, how do we know whether it's towards the y-axis or the x-axis? If there's no rotation.
So in that first one, that's towards the x direction. Right?
What notation is used to know that?
Well, remember that x, y, and yx are identical. So, like, it's just a matter of how you set your coordinate system. To be 100% clear here, memorizing these will not matter. But the idea is internalizing how the fluid moves does matter. Okay? So you won't be required on any homework to get exactly, okay, I got it in the right direction. You'll just have an intuitive sense, oh, they're moving towards each other. That make sense?
Could you get the second image without rotation, with just strain?
With the second one?
Yeah.
No.
Okay, so you need a rotation.
You need a rotation and a strain. Now, if I rotate my head, okay, fine, right? But do you see how they require both in order to be, right? When we talk about Galilean transformations, this discussion of kinematics as a whole, there is an actual difference between those two pictures, right? Okay. Happy? Unhappy? Raise your hand if you're cranky. Okay, raise your hand if you're always cranky. Okay, good. All right. Nothing. Okay. So we talk about the rotation tensor. You can define it in a really fun way. Okay. There's no erasers on this side, and what, all of them on this side? So in fact, when we talk about a fluid, when we talk about the rotation forms, we can make this really fun mathematical construct. And say Rij, that's the rotation tensor, right? I'm going to call it minus Levi-Civicje. Omega k. What is the Levi-Civicje symbol?
So,
How do you pronounce it?
Yeah.
No way.
no.
How do you say it?
Sevita.
Okay.
Like
You
Sevita.
is not Italian? Ceviche?
Yeah.
Yes.
Yeah, no, that's a Mexican dish.
Ceviche? No. All right, say it however you want. I don't care. It's not Lagrange. You don't have to get it right. But it's your favorite tensor. Why? What? No. Because it's the easiest. Yeah, it's super easy. So why is it super easy?
So simple, we should talk.
It's honestly so simple, we should not even talk about it. When two of them are the same, you get 0. Oh, sorry, when all three are the same, you get 0. Right? And when two of them are different, you get like -1 or 1, depending on how you feel that day. Okay? So something like this, I think looks something like this. All of those are 1s, sorry. Yeah, check me on that, but I think that's right. And you can make it as many variables as you want. What we're gonna do here is we're gonna use this fun little W. We're gonna add them in here. And it's gonna give you something that looks like this. Okay. Is that symmetric? No, it's by definition, right? Okay. If we recall over there, Rij is what gave us these W's, right? In the direction that they're supposed to be. So that stuff over there, that differentials of this thing U kind of looks a little familiar, right? No? Never seen it before. It's the equation for curl. Okay. So in fact, we can write. Correct? What is a curl? Cross product of the gradient? Is that correct? Or gradient of the cross product? That order matters, right? Gradient cross product. Okay. Okay, so every single term that's in here comes from doing this, which looks, hey, just like that. So even though I started off with something that was garbage and pulled out of my butt, it turns out to have a meaning. And there's a way to interpret this. What is this word called? Close. I like that thought, but no. Curlness? That's fun. I like that too. Yeah. Are you reading that or did you think of it? When you're looking down at your screen while you say it, it really doesn't sell it. But yes, that's absolutely correct. Okay. So it's the vorticity. And what that really is saying is, how is the fluid ripping? Right? Is it okay? Okay. So let me ask you a different question. If omega equals 0, what does that mean? Doesn't? No?
It doesn't, you have to do it, you have to do it.
Commit to the bit. Commit, there you go. It doesn't, which is? There's no rotation. So the fluid must be, no, don't think stationary. Stationary is not the way to think of a fluid. Imagine a pipe in which flow is going through it like this. Let's not jump ahead of ourselves here. Hold on. Everyone, don't jump ahead of yourself. Look at those rotational terms, okay? du dx, the flow through a pipe. This is a two-dimensional problem, okay? Imagine the flow is not changing in the x direction, same fluid velocity, and same fluid velocity in y. What's your r terms? 0, everywhere 0. The fluid is not rotating, but it certainly is moving. Okay, steadiness, unsteadiness, we haven't talked about that yet. Don't worry about that. Okay. So when the vorticity is 0, we call the fluid. What? Chew. Yes, I'm waiting for the answer.
Non-vorticity.
Non-rotational, and we like to use fancy words here, so we call it irrotation. Irritable, Mateo, irritation. Okay? Does that make sense? Now, you may have seen this before, right? Maybe you've seen del crossed with something, and you might even have seen something like this, where del cross u equals 0. What does that tell you you can do?
Gradient of a scalar?
The gradient of a scalar. So I can write u as the gradient of something, because the gradient of the cross of a gradient is by definition 0. And you can prove that to yourself at home. Okay, so this is actually super helpful, because rather than having to define the velocity at every single location, I can just find this function sometimes, thankfully called the stream function, and I can just work backwards, as long as the fluid is irrotational. Okay? Yeah.
What was the fancy word for that? Irrotational?
Irrotational.
It was one with vorticity.
So this is the condition for irrotational, and this is the definition of the we built vorticity, right? On rock and roll. Yeah. So hopefully some of this looks familiar. You may have seen this stuff before. This stuff before. These are Maxwell's equations. So if you set this equal to 0, that means that you have what type of problem?
Electrostatics.
An electrostatic problem. It's not an electrodynamic problem. We love electrostatics. Those are super easy. But they're at least like solvable. That means that you can copy and paste the solution as long as it looks like this looked, right? So in fact, when we look at a fluid, say you have some conductor and you pass it through a magnetic field. Holy shit, that looks really similar to the way that fluid goes around a rock in a stream. And it turns out they're mathematically equivalent. Okay? Why? Because they use fields. Okay? So field formalism is really important. Another way of looking at this, you can say if del dot v equals 0, right? Then del cross v will equal to vorticity. By definition, right? And you can use the potential formalism to find v everywhere. Okay, we have enough time.
Wait, are we treating that as physics?
No. Sorry. There is a similarity in the mathematics in specific conditions. Okay? This is not always true. 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 Sometimes fluids will look like the solutions to E&M. That's all I'm trying to say. Do not read more into it. Okay. You don't have, okay, so we have things here like the definition of no magnetic monopoles, right? That obviously doesn't exist for a fluid parcel. Fluid parcels are just things moving around. The point is that there are field formalisms. That is a way of saying, I know the properties of the fluid everywhere because they're all connected. Similarly, a magnetic charge or an electric charge, place it into space and its potential lines are everywhere instantaneously. Now, of course, that's not exactly right, but you know what I'm saying, right? So things like Electric field lines describe how a particle will move with respect to another particle. If you place an object into a fluid, you know exactly how that object will move because of streamlines. Streamlines are provided by stream functions. That make sense? Yeah. Oh, okay. Questions? Okay. All right. One more problem. Write what happens to the fluid parcel under this fluid velocity. Now, here's what you're going to do. Okay. You're going to draw this picture. A, B, C, Q, all these ones. And just a few seconds later, under the influence of this differential fluid flow. So do it intuitively, right? Right, what happens to the fluid parcel? Yeah. You're gonna write what happens to this parcel. We're gonna imagine we have a parcel. It's a very special parcel. Okay. This parcel, we put red dye into it, and this parcel, we put blue dye into it. Okay. When we start the experiment, and the flow is moving where this is moving faster up here, and this is moving slower down here. And we look a few seconds later, how does this look right here? And we're going to draw that picture so that the colors are all maintained. What's that? Yes, but they won't mix. They will push on each other potentially, but they won't circulate into it. Yeah. Just to yourself, not yet. Don't work together yet. Just write it down for yourself so you can test your own understanding. You should have a picture written down, like a picture that you'll be able to compare to what we're about to see. To draw a picture, just insert drawing. Okay, well then, I don't know what to tell you. You need a piece of paper?
Is it flowing like this, like the whole time? Is it flowing upwards or is it?
No. The flow is only moving to the right. But the length of the arrows, remember, this is a vector quantity. So this is moving faster than this is moving. Flow is only moving to the right. When you have a picture, just hold it up to me. Okay. I'm gonna strain to look at you because my eyes are bad. That doesn't mean that I'm judging your picture. I should bring a little telescope. Let me see. Okay. I can't see it good. Is it up higher? Don't show anyone else. Don't look. Okay. 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 Good picture? Yeah. You sure? Read, you're canceled. Okay, so it's good to read the book before you come, but you don't have to read the book while I'm reading. Okay. Okay. Just waiting on a couple more. Okay. There you go. Are you gonna flip it around? Okay, okay. All right, all right. How are folks feeling? You think you nailed it? Raise your hand if you nailed it. Awesome, awesome. A lot of confidence. Is that what you got? So I saw a lot of people. A lot of people moved, like, say, B downwards or C downwards and rotated the fluid parcel. Is there rotation here? Why? You can get there, believe me. Let's look at that rotation term for a second, okay? So this is certainly changing in this direction, right? Is there flow in Y? There is no flow in Y. Oh. There's no flow in the direction of Y, yeah.
So in this case, would it be like, the rotation would be R00? If it's
Well, R00 is identically 0, right? So there's no rotation in 0, right? And in fact, if you look at all of the terms, because there's only flow in one direction, they're all 0. So there can't be rotation in this fluid, right? Okay, so now I'm going to really bother you and make you upset. Okay. So if you look in the bottom left-hand corner, you'll see that in fact, the coordinate system is rotated. So now I want you to do this with me, and I want you to rotate your head. And as you rotate your head, you'll notice that in fact, there is a Y and an X component of the velocity now. And now rotations can occur, right? So now when you look with your head tilted, there is a rotation in the fluid. And this box here just becomes stretched along the parallel axis. So whereas before, oh shit, whereas before here, it looks like it's weirdly pulled to the side, like, whoop. When I rotate my head, you just stretched it. That's all I did. You see this? So there's an intrinsic linking between the rotation, the strains, and the stresses in a fluid parcel. So when you first started this problem, there was just strains of the fluid parcel moving this axis towards this axis, just like I had over here, right? That was a strain. Boom. But I rotate my head, and it's a different strain along the principal axis, X. Right? Notice that this X1 is oriented with X1. Okay, that's as much information as I can ram into you. I have to let you go now. But if you have any questions, I'm happy to answer them. Yeah.
Why did they hit that square not? Like, why is it not blinded?
It is slanted.
Huh?
Yeah, look, it's totally tilted. What are you talking about?
They're all it's straight, it's not slanted.
This becomes that. And then this becomes this. Lengthened in this direction,
Oh,
but it's definitely tilted with respect to its original direction.
Yeah.
It's lengthened in the direction of the principal axis for sure. But you're right that there's still a right angle here.
right, yeah.
Yeah, you didn't like the right angle. That's fair.
Yeah.
But the angle itself changed,
Yeah.
right, with respect to where it was originally. This line became more shallow.
I did not like the right angle.
Okay, give me your homeworks.
Oh, yeah.
Shit. I did go over that, and I will go over it again this week if people want. I can also just talk about it briefly here if people want.
Sorry.
What?
Oh, I didn't finish it there.
Well, if you haven't finished it, give it to me later. There's no deadlines, but
Oh, really?
well, I mean, if you don't do it, I would prefer that you do the work. The reason that I said there are deadlines in a class in which there are no grading is that I want to keep you on track. If you don't do it in time, that's a warning to yourself that you don't have enough time, right?
I just didn't do like.
You want me to just give you this and give me 1.2 later, 1.20?
Sure.
Oh, yeah. Yeah, we don't mind that. then.
Okay, so no one, who's done 1.2? 20, 1.20. Okay, so no one's done one, so I'll just accept whatever you have now and I'll get the rest from you later.
Okay.
Thank you.
We can still work on the rest.
I mean, you have more homework coming, so just make sure you don't, you know.
Yeah, it's like.
Mm, there you go. Did you bring that or is that there? Oh, okay. That's preparedness.